we got to finish off the last lecture with a quote by Newton. And what this is, Newton is so famous, and Newton was able to encapsulate the fundamental, pretty much all, like for sure, everything about classical mechanics is embodied in that one equation. Force equals mass times acceleration. It took Newton a long time. I can't remember. It was like multiple months, possibly a few years, where he basically became obsessed and just focused on trying to figure out what's the essence of what's this whole idea about how things move. And this is like partway through, he was trying to condense this. I think at one point he had like 26 laws, and he was trying to condense this into the smallest thing he could. And so at this point, he was up to 3. He was down to 3. And you're going to see in one of these, it's kind of awkward. It's like, it's very long words that kind of repeat themselves. And you can kind of tell it's like he's still trying to figure all this stuff out. Because sometimes I think it's helpful to see this, because oftentimes we only get presented the final result and it looks so simple. And it's elegantly simple, but it's very rare that stuff just comes into your head. Einstein didn't just sit down one day over coffee and say E equals mc squared. So here we go. Number 1, first law. Every body proceeds uniformly in a right line to infinity unless something extrinsic hinders it, right? So body. Now we got to start to define body. It's like a thing. That's what he was thinking in his head. Any kind of thing, like an object, once it starts moving, the default is it's always going to move forever. The only thing that's going to make it change is if something external to it. He doesn't even know what that is. Doesn't know what it is. He eventually came to the idea that was a force, and he defined force, the whole concept of force. So, but what he's thinking in his head is, right, we got these things and they move. And the key thing is, the fundamental thing is they keep moving, not that they're just stopped. Once they're moving, they move forever unless something acts on it, right? Now, here's this one. The red is my stuff, right? So what does it do? The motion is going to change because something is hindering it. So there we go. It's proportional to the impressed force. That's the external again. The impressed force, something from the outside. So the change happens in the direction perpendicular or in the right line in which that force is impressed. And so what that actually means is that acceleration and force are vectors, right? That's a whole other interesting concept. And of course, acceleration, he had to develop calculus to be able to even have the idea of an acceleration, right? And then that next one about the inherent, innate, and essential force of a body is the power. He was trying to get at this word by which it perseveres in its state of resting or moving uniformly. And that power, the ability of it to sort of like not want to be changed, is related to, again, he didn't have mass. He says quantity of the body. The heck is this, right? So he had to quantify like what is the thing in a body that makes it want to resist being changed from where it's going, right? And there it is. It is actually exerted proportional to the change. This last sentence is basically a repetition of the previous thing. And then there had to be this thing. This is just one body. So what if you got more than one? And this is so cool. That's all you need. If one of them pushes against another one, it's going to push back the same way, right? This stuff all seems so completely trivial and obvious. And that's why it's so amazing, elegant, because it's in capturing so much stuff. So, and if you're interested, this is a biography, a biography written by someone else, of course, in the 90s about Isaac Newton. So, any thoughts? Make sense? Interesting? Kind of? Dumb? Somebody? Yeah? No? Ayat?
Yes. Well, I mean, a Newton law, I haven't done a lot with it, like before, but now
Oh,
it it makes more says to me the more I do with PFC and my research.
Yeah.
Um, but
Yeah.
yeah,
Because yeah, I mean, this is a PFC is simply a computational way of applying this to bodies, right? So,
yeah,
right, F equals ma, that's number two. 1 and 2 are kind of combined in that. And then you got this idea, what if a body actually interacts with another body, right? And so, oh, this thing that Newton came up with to quantify called a force, and it's a vector. That builds up, and it's the same, equal and opposite, right?
yeah.
So, quote of the day, here we go. We're going to finish this. We're going to go pretty quick. And what we're going to do is just actually use the material modeling support package. In the process of using it, you'll get introduced to it from a hands-on level. It's almost like, you know, if you were working in a wood shop and you were learning how to build a chair, you first have to go through all this stuff about how does the table saw work. And that's kind of what we've done. And now we're going to actually say, let's actually fire up that table saw, and I'll show you some little things about how to run it. And then we're going to talk about, we really want to talk about that subspring network breakable Voronoi model. Before we do that, we just have a few slides that put PFC and bonded particle modeling in the larger context of microstructural rock models. It's not the only game in town. There are other ways of building microstructural models and realizing them computationally. So I'm just going to super big high level touch on that. Okay. So remember, we talked about the material modeling package, but we only talked about it in slides. Now we're going to actually try to use it. So use it to calibrate something. So we'll set the stage here. So here we go. Wouldn't it be fun if we could all go on a field trip and go check this out, right? There it is, Cascade Sandstone. Why do we care about Cascade Sandstone in the oil industry? This is one of the sandstones that they use repeatedly to do tests on. And everybody uses the same one because that way you can write papers about it and you can compare and get a better idea of, you know, comparisons of this. Another one is Table Rock Sandstone. Another one is Torrey Buff Sandstone. So you can actually go to a store and you could order this stuff online and they'll send you a hunk. I think this is 50 millimeter diameter. I'm not sure, but that's a cross section of a specimen. And at this scale, that's what it looks like. I had an opportunity to work with people at BP, the big oil company, some years ago. And so then I got to see the next level of this because now they're a real oil company. Now they're going to go zoom in on this to try to understand more of the microstructure. And they call that petrology. So they can do things like this. These are thin sections through that rock. Notice the length scale. Look at the left one. That's a 0.5 millimeter, right? So these grains, if that it's you can certainly call these things grains. They seem to be discrete bodies. The pink is epoxy. So the pink is actually void region. And they take the sample and then they inject the epoxy and it hardens. And that allows them to cut the sample perpendicular to the axis usually, and then make a couple of cuts and get a thin section out of it and shine light through it. And so here we have this. You zoom in even more. That's 100 microns. You see this. These grains are certainly complicated, to say the least. It's a very weird thing. Like, you know, even just what's the shape of these grains? There are a whole bunch of different shapes here. They're angular. They're definitely angular, most of them. This has not been washed down a lot of creeks before it got cemented together. That's why it's still angular. And even like, what's the size? If you take sort of the median, like half of them are bigger, half of them are smaller. That median is 50 microns. No, wait. Yes. It's considered to be 50 microns. This is 100 microns. So we're on the, if you take the average of everything, they're about 50 microns. It's like crazy small. Your hair is about 50 micron diameter, a piece of human hair. And so this is the stuff. This is basically what the guys in the oil industry have to work with when they try to make predictions of, you know, I make a borehole, is it going to start to unravel or not? And they use this as much as they can. And the ones who are doing microstructural modeling like we are always trying to somehow relate this real microstructure to a model, which is always a simplification, right? And so the data that they have is pretty much the data that they can get. So one of the things that seems to be important here is size distribution of this stuff. And I don't have a plot with me right now to show you, but there is, you know, they do these things. They somehow get size distributions of this. And then, you know, that's definitely tells you all sorts of stuff about how it's going to behave. So they have size distribution and they have images like this. And it's like, okay, here we go. Like maybe when I'm no longer alive and you guys are as old as me, we'll have the kind of microstructural modeling where we could actually just take this scan and we could just pretty much almost one-to-one reproduce this as a model, right? We could already do this with PFC if you just make a huge number of particles and pack them together that are much, much smaller than the average grain, than the smallest grain, and then you just lay these on top, and then you get these clusters that'll behave like grains, right? And they're deformable, they're breakable. It's not perfect, but you know, people have done that. But the problem is, you know, you're limited, maybe 1 million particles of those little guys. So that's what it looks like. And so our task is, can we make this? So we have to choose what contact model to use. And there's not very many of them. There hasn't been a lot of work done in this area. So we got what we got. So let's just use parallel bonds. And this is my best way of coming up with a physical manifestation to show how does a parallel bond behave. And it pretty much behaves like unbreakable beads with circular cross-section cement of different radiuses. And that cement is either completely okay or it breaks. When it reaches a critical state, it breaks instantly, which is also a pretty big assumption. You would think that as this guy here started getting damaged, it would start to slowly unravel itself. So we're going to have this very, very crude, simplified model of that. So the question is, can we make this dance like this? That's the goal. And a complete realistic assessment is that not really. Come on, look at that thing on the left. You're going to have additional microstructural features if you want to capture all of the response of this real system. And so what we end up doing then is we essentially say, well, let's try to look at this in a much more far away view. Let's try to think of it like this. And now we're starting to think of it as, oh, this collection of things is really just kind of a bunch of big stuff that's kind of at the macro scale supposed to behave like a specimen. And then we say, well, and we're also doing rock mechanics. And so what are the important properties of a specimen? And we talk about deformability. And deformability is Young's modulus, Poisson ratio. And then we talk about UCS tests. And this is the point at which it fails. And then we talk about tension tests. And this is the point at which it fails. So at a sort of a minimum, you would say we would really like to match these things, right? And of course, it's even more complicated than that because Young's modulus and Poisson ratio, the material rock does not actually behave like a perfect linear elastic isotropic material because it changes. Those things change based on how you load it. If you pull it apart, it has less guys in contact and the Young's modulus gets lower. And like for a granite, it might be 80% less when you do a tension pull and measure it than if you do a compression. That's why we got the CC here. This is an E and a nu that's measured by doing a UCS test. And this is a tensile strength that's measured by doing a tension test, right? And so the material modeling support package gives us a tool that's put together all the sorts of things that you need to build a material in a clear and well-defined way, and then to do UCS tests and tension tests. And you could do triaxial tests. So this would be like the goal. So then you say it's a parallel bond model. So in the end, these are what I was referring to as contact properties. This is just the properties of the model itself that only relates to one piece of cement. And then, as I also was talking before, there's ensemble properties on top of this, right? Like how many guys are cemented? How are the gaps filled with cement? Are they not? All those kind of things, right? I'm not putting that on here. But you get the idea. There's all those different things we can play with in order to make this here dance like this, right? So we're saying, oh, what if you took these and perfectly glued every single gap within a certain distance and put in cement? Oh, but what if you took out a bunch of that at certain gaps? Well, they're going to be different, right? So we're doing the best we can with that guy. So, and then here is a roadmap that I talked about a little bit last time about how to go about matching these properties we discussed. So these are the contact parameters, and we're going to choose these to match E. We're going to choose those to match nu. That's going to kind of be the first thing we do, because you got to get the right stiffness to begin with. If the thing has the stiffness of a marshmallow, it's not going to make any sense to do a direct tension and UCS test on it. And then you're going to do a direct tension test and measure the tensile strength. And in the end, that's going to mean we're going to choose the microtensile strength so that we can match the macrotensile strength. Meanwhile, we're keeping the shear strength. We're keeping the shear strength infinite. So we're going to make that sucker so that it can't fail in shear. We're going to only let it fail in tension. If it only fails in tension, the only thing that matters is the tensile strength. So thus we can do a calibration. Measure this. It's 2 times too big. Make this 2 times smaller. Probably pretty much get it. Then we're going to go and we're going to do a UCS test to measure the UCS. So we'll just take this exact thing with the value we have, run the UCS test, and now we're going to have a free parameter, which is going to be that cohesion. And the cohesion is that controls the shear strength. Remember, we started, the material can't fail in shear. So, but we have to let it, rock is going to have some failure, typically near the peak. In a UCS test, you start to get some micro shear failure. And that micro shear failure allows the system, the entire specimen, to form a coherent fracture or shear band so that it actually fails. And so therefore, we can start to, like now, instead of having it be infinity, we make it smaller and smaller. Eventually, we're going to get some shear failure. And so that's going to let us control the UCS, but only to a certain extent. Because once we have, even if we have the shear strength infinite and we choose the tensile strength to match the direct tension strength, now we're done. We can't change that. We just keep it infinite. We do a test, a UCS test, and even then it's going to fail. And for a parallel bond, it's going to fail at about 5 times the tensile strength. So the only thing we can do if we also allow it to fail in shear is we can make this smaller. And, you know, maybe there certainly are sandstones that have a UCS that's not 5 times the tensile. It might be 2 or 3. Most competent sandstones, though, don't. So that's a limitation that we have with the parallel bond. And then the last idea is to say, now we fix both of these other 2 guys that we've got. And the last thing left is we can play with this internal friction angle. And again, to some extent, that will control how the material increases its strength when you start to do confinement. And I was characterizing it by this phi, this psi. I think this is called psi. Yes, this is called psi. And we talked about, remember, some people use a Hook-Brown to describe this relationship. Some people use a friction angle and cohesion to do it. The key thing is that when you load a rock in triaxial compression, the more you confine it, the higher the strength is, which is defined as the point at which the stress strain curve doesn't go up anymore. So this is our world. We're not going to have time. See, if we had the real class, this would be fun, because then I'd like spend a little time, and then I'd say, okay, for the next week now, go and screw around with this thing, and you could all come up with something to see how close you could get to this stuff. We're just going to do a quick walkthrough of the first part of doing this. Okay, with me? Yes, yes?
Yes.
Guys out there? Here we go. Okay, good. So we're going to have to look at this material modeling support package. And what you're going to find is one magic data file that we can call, and you can probably figure out what it does. This is going to just work with PFC2D, and we have a set of example projects. You want to start with those if you're going to start working with this. And so for each of the different types of materials we can build, parallel bonded material, flat jointed material, for each one, there's an example project. And that creates a specimen that's as small as possible, the least number of particles possible, to still give you the basic response of the system. And so these things are made to run fast and to use as a starting point. And if you call this magic file, what it's going to do, it's going to fire up PFC, and then that PFC is going to fire up another PFC and run that project. And when that's all done, it's going to shut down, it's going to fire up another one, and it's going to run that project. And each of the projects it's running, it's going to go in a directory where it's parallel bond stuff. And in there, it's going to fire up a PFC and do the creation of the material. And then it's going to go, when that's done, and fire up another PFC and do a direct tension test. And then when that's done, it's going to come back and do a UCS test, etc. So we can, this will be our starting point. So let's go and actually look at this. If you get the material modeling support package, it's a directory, package 9.3. So material modeling package, that's what that means. So the entire thing is in this one directory, okay? And at the very top, it's got a README. And this is the basic high-level description. What's the capabilities, and then how do you use this in the details? Where do you put where, stuff like that. Here's where the example projects are, right? And then, of course, good luck. Have fun. That's the high level. Then we're going to find that, and there's going to be a contents. This is all the stuff and how it's laid out. There's a whole documentation set of things. And then there's these example projects. And so you can see there a directory with just 2D ones that work with PFC2D, and a completely separate directory with 3D projects that just work with PFC3D. Okay. And it says this works with PFC version 9. And notice it says package 9 dot, it's got some number. That number is, think of it like a release. This is like a program. This is a functionality. It's built upon a certain version of PFC. If we go and add capability to this package, well, instead of being 9.2, it has to become 9.3. And so that's, again, at the high level here, public modifications. And so here you go. This is package 9.3. It was tested with this version of PFC at this date. And then it's got all the different descriptions of what happened. Here's enhancements, way back at 9.2, back in January, you updated things, etc. So this is basically the modifications list, right? Any program should have these things, right? You just got a new subversion of it. And PFC at the highest level, the program itself, when you get the late, instead of having 9.0.180, there's going to be at some point 0.181. That's like a subversion, and there's a file just like this that talks about, here's the changes that were made to the program. Okay, with me?
Yep.
Go into documentation. Package documentation. here we go. These are all the documents that are in this documentation directory. Okay. One of the important ones is support. This support memo, here we go. This is the technical memo that describes this package. And notice it says package 9.3. Okay. This is a full-blown, proper description of everything that's going on here. This thing is 87 pages. Okay. And it's got everything laid out about what's going on with these models. And in particular, it defines the well-defined set of properties for these models, right? There's the fish function name or the fish variable name. Here's what we're calling it. And then in the text, it talks about what is this, things like that. Okay. So that's your roadmap to do this. There's also related to this memo, example material memo. And this guy, here we go, gives you examples of granular materials or bonded materials, contact bonded, parallel bonded, flat jointed, right? 2D and 3D. So if we go, for example, parallel bonded material, 2D discs, page 21, that's the one we're going to be working with. And it's right here. It talks about this. The example is in a directory called Material Genesis Parallel Bond 2D. We'll find that directory. We're going to run that, and we're going to find that here's all the microproperties of the contacts. This is what it's going to create. Here's a way of looking at the bonds as lines. The width, the radius is the radius of the bond, right? And then here's the kind of results it's going to give us, right? We're going to do an unconfined UCS test. And from that test, we're going to manually screw around and take these slopes and things to give us the modulus, strength, etc. Okay. So that's the high level world. And so if we're going to actually work with this, we're going to go into example projects 2D, run all. Oh, sorry. Okay, so that's actually not there. What's there is example projects 2D and example projects 3D. So what I did is I took this and copied it and renamed it to be run all. And then I went, and at the very top of this, here's all the each directory, like this one makes a parallel bonded 2D material and tests it. It's all the stuff, it's in that directory. The outer level is a project, example projects run. Let me just open that up. And take a minute here to wake up. And here's the data file. Just got one data file. And it does a model new. And this is this interesting PFC internal command. This is actually sending a command to the operating system. And it's saying clone yourself. So take yourself. Yourself means PFC, the PFC executable. Clone yourself, make another PFC executable, which means it's going to start a separate instance of PFC, like running in its own window, totally different. And it's going to, when that's going to fire up and it's going to open this project, and then it's going to call this data file. And as we'll see, that's going to be doing the, that's going to do a linear example. That's in the linear directory. Eventually, it's going to go to the parallel bond directory. And so this system command, it's going to be in the manual somewhere, talking about it. It's going to fire this up, and when this data file is completely done, it has an exit in it, which means it shuts down. So then that clone shuts down, and now this guy, this PFC, gets control again, and then it does the next one. Okay. So this is actually what we're almost always doing when we're running PFC. We're working with fish and the editor and making a data files that you can eventually set them up so that you can just run the whole file. And you're usually going to do multiple things, like you might do a parameter study. You might run it get results, and then you want to run it again, but just change one parameter and get results. So this way you can do that. You make two directories that you want, and then at this level you can call this. So it'll go and do one, and then it'll do the other, etc. Okay. So this is a very useful thing. And so in this P-bond thing, it then ran everything. But before we do that, let's just do it. There, that's what you got. Let's drill into the P-bond 2D directory, and this is what's there to begin with. So here we go, material genesis. So I'm going to fire up PFC. And so this is the top level data file. And it talks about it's going to use two other data files to have parameters. MV, material vessel parameters. How big is the specimen? How stiff is the walls of the specimen? Material property parameters. What are all those contact values, right? It's going to make certain save files. Okay, all that stuff. This is an attempt to describe what it's going to do. And then here's the code right there. And you guys know fish now. You could work your way through. Eventually, it's going to do a model new, start all over. It's going to call in certain data files. I use the convention .fis if that data file just has fish functions. And then I use the thing like p2dat if it's a PFC2D data file, right? And so it's going to call those in, and then it's going to start calling functions that are inside of those files. Material vessel, make a material vessel. Make the material itself, material property, make. And then these guys are going to list out properties and micro properties, things like that. So when I run this, material vessel, look at this. There it is, MV params, look on the left there. There we go. It's going to define a fish function and then call the fish function. And in the fish function, it's setting the properties. This is the vessel height. This is the vessel width. This is the effective modulus at the interface between vessel and the particles. Okay. This corresponds with the memo of the documentation. So we go in there and we go to material modeling support memo, and we find where we call these common properties, common material properties, 18. Here we go. Material type is okay. Wait, this is not, we're not there yet. These are actually material genesis, the whole process of making the material. Material genesis procedure, where is these? It must be there. Here's the material vessels. Here we go. Right, so for example, right here, material vessel, height, width, and depth. Where is it? Right there. So that's the fish thing. Height, width, and depth. Sorry about that. And so then there's the picture in 2D. That's the height. That's the width. The depth is always 1 in a 2D model, right? And so there's different material vessels, their parameters. There we go. So we're going to make a vessel that's going to be square, and it's going to be 50 millimeters. And this package is assuming you're always using SI units, only because when it makes plots, it's going to put like pascals or meters, things like that on there. So make the vessel. Now assign all the material properties. So that's this guy, MP params. And here we go. These are common here's the grain size distribution. Minimum diameter, maximum diameter, etc. Okay. Packing parameters. We're going to pack this at a certain material pressure, if you recall. So we get an isotropic. We have to pack it. So we're going to pack it to 30 MPa. We're not going to have time to talk about these other things. They're described in the memo. And then finally, after it's packed, we're going to assign properties to the parallel bonds themselves. And you may recall the parallel bonds have two springs. They have the linear springs and the parallel bond springs. So that means we have to have properties for the linear springs and for the separate ones. So we have the linear group, the parallel bond group. Okay. And then in the future, if new contacts form that weren't there before, we have to know what to do. So this package is going to create a new contact and give it a linear contact model. Because if we just think, oh, they're not sticky, they're just the new surfaces, they're pushing together, they're just going to behave like frictional surfaces. And so they're going to have a Kn and a Ks and a friction. And you may also recall, in this case, we're not giving the Kn and Ks directly, we're giving an effective modulus and a stiffness ratio. So this is what's all going to happen. Let's just run this thing. At the end of this, it says program exit. It'll shut down PFC. I'm going to comment that out because I don't want it to shut down. So I'm running it. I got plots set up. This is the material vessel plot. Look, it says material vessel. It's showing force chains. Whoa, it's done. It already built the whole thing. It's going so fast we can't really see what's going on. Let's do this again. It made a cloud of particles. It's packing them. It's reaching some equilibrium tolerance, and now it's put in all the bonds. So now you have a save file. You have two save files out there. One of them still has the walls on it. The other one has the walls removed. And this is that microstructural box that we're going to use so we can zoom in, look at those cool plots that show like what does a parallel bond look like and stuff like that. And we've also got some other things. We've got particle size distribution window. And so here we go, mass passing between 0 and 100%, and this is particle size. And you can read, there's other things here too. So this is like a built-in thing, right? The material properties, one of the ones way up at the top is a string. It's the material. We're going to give it that name. SS, parallel bonded 2D. And therefore, in all the plots, it's going to say that. So it says that material, it's been removed from the physical vessel. Cool. I go to the other one where the walls, it's the material in the physical vessel. So every single plot you see, every window is going to have a meaningful title. Okay. And so then I'll just shut this down. Keep that going. Go back up to where we were. So we were running this thing, PBond 2D. And so now we got those two save files. So now we got it separate directories to do the separate tests. We can do a compression test, which is really a triaxial test. You can run it in a mode where there's no sidewalls. That's like a UCS test then. Compression test, tensile test, that's a direct tension test. And then we also have the ability to do a diametral compression test. In the rock mechanics world, they call it a Brazilian test. So let's go into the tensile test one. And here we go. Oh, notice every directory also has a text file, directory contents. So here's the directory name, and here are the files that are in it, a data file, a project file, etc. So let's fire up the project. This is the tensile test project. So what's it going to do? It's going to restore the save file from one level up, and then it's going to do a test on it. So you can see here, model restore. And also every save file, there's a naming convention. You can give it a name. You could have called this Castlegate 6. Or if you don't give it a name, it just calls it this, PFC mat dash material. Okay. So it restores the previous model. It loads in some more functions that it's going to use. And it has parameters for the test, TT params, tensile test parameters. Here you go. And again, there's a whole thing in there about doing a tensile test. Where is it? Laboratory test. Direct tension test, page 74. Here it is, direct tension test parameters. Here's what they are, right? One of them, for example, is the thickness that we're going to create a bunch, we're going to grab particles on the top and bottom, certain layer of them of a certain thickness, and then we're going to use those and pull it apart. And here's the strain rate that we're applying. We've talked about how important this is. That's how fast the thing's getting pulled apart. And then we can, all of these tests are set up. You can either run them so they stop automatically when the stress has dropped to a certain fraction of the peak that it ever reached, or you can tell it to do stages. Apply this much strain, then apply that much strain, then apply that much strain. Okay. So there we go. We're setting different things here. This is the strain rate. There's a multiplier just to make it nice. If you want to run the test faster, you just change the multiplier. It's setting up some histories, right? So let's just run this thing. And again, I don't want it to stop. So I'm going to run this. Let's just do this right there, right at the beginning. Put a return. It's going to restore the model and load in some fish functions. So one of my plots, TT specimen, that's the parallel bonded material that's been removed from the physical vessel. That was that save file, one level up, that we built before, right? So let's actually run this thing now. That's the displacement field. We're pulling it apart. It's the displacement vector of each particle in there. Here's another plot. That's the axial stress that's being resulting that you're pulling with. This is the axial strain. So that's the stress strain curve. It's running the test right now. It even says axial stress versus axial strain. What's the strain rate? It's telling you all that stuff. Boom. Just did this. Let's look at it. Let's turn off the displacements. Contact force chains. Here we go. Tension is red. Compression is black. We're pulling it apart. It's mostly tension. Looks like something weird happened in the middle here. Well, we can turn on the fracture. Boom, let's turn off the balls. Those are the bonds that are broken. Let's make the color be red for tension failure. It says parallel bond tension failure. If some of them had broken in shear, there'd be another color, and it would say shear failure. If I turn the balls back on and I get rid of the outline, you can see these are bonds that have broken in that test. And in this case, they started near the middle, and now they're working their way out. As they do that, look, there's no more tension going across them, right? They're getting higher tension here. That's why it keeps on, it doesn't stop. It just goes all the way across. Meanwhile, that's the force we're measuring. And we told this test to stop at when this value is 80% of that. If I change this, instead of going to 80%, let's go to 0.10%. Let's run it again. There's the displacements, right? We're going to keep on going now. Boom. Now the stress strain curve, we kept on running. So now it's gone, it's almost fully unloaded because we've got that sucker, it's ripped all the way across. If we look at the forces, chains, there's still a little bit of tension carried here. I got to run it a little further and then it'll be in two pieces. These forces will be zero. Okay. Look at draw them as a group. And we can see the different, though, those guys. Oh, come on. Let's make this one gray. And let's make this one yellow. There. This is saying this is the top guys. This is the bottom guys. Those are the guys that are being controlled, that are being pulled. And then we're, and in this case, we're using a measurement circle. We got measurement circle based load here. This is actually axial stress is based on measurements, but the axial strain that we're plotting, this one is based on boundary based. And what that means is that it's looking at the motion of these boundaries versus it's taking change in length over length. And so therefore, this is what you would be measuring actually in if you did a real tension test. You would be measuring how much you're pulling it apart, right? And that's why this then just drops. Pulling it just a tiny bit more, and that thing rips across, and the stress goes all the way down to 0. You also, though, could be using a measurement. Now the axial strain is based on a measurement circle. So that means that there's actually a measurement circle. Add a new plot item. Where's that measurement thing? Measure. There's actually a measurement circle here. And so now this is measuring the strains by averaging the motion of the particles inside of it. That's then what this is. And this is not brittle now because if you think about it, when you measure it that way, when this thing starts to fail, this material starts sucking back together a little bit. And so it ends up changing the characteristics of this. You never see these in labs because in laboratory, they can't measure the internal deformation. Instead, in the laboratory, your curves look like this because they're measuring the motion of the platens. Enough said. We're going fast here. Is this making sense?
Yes.
Yes.
Yes? Okay. So here's, again, stress strain curve. Here's another plot. This is the cracking. And so we're tracking. And here is tensile breakages. The number of tensile breakages are being plotted in green. The number of shear in red. The sum of the two is this. In this case, they're all tensile breakages. So number of cracks, again, versus axial strain. Okay, this is often a useful bit of information here. Okay, so that's my tensile test. Let's do a quick view of the UCS test. So now let's look at that. Let's run that. Here's a compression test. So it's all the same idea. You're going to have parameters. This stuff is all set up the same way, right? So you're going to have parameters that control the test. It's going to restore the exact same specimen from one level above, right? And that's going to do the test. And again, it has parameters. Here is that strain rate. Super important thing. Here's a view of the system. There's no, doesn't have anything in there, right? Yet. So let's just run it. Let's comment. We don't want it to stop, to shut down. Here we go. The first thing it's going to do is move those away, and then it starts pushing together. And these are the force chains. Now let me run that again. Watch what happens with the force chains. To begin with, there's no load. But you're going to see how it starts to push from the outside in, and now we've got this force chain system. Black is compression. In this case, pink is tension. Here's a stress strain curve. This is deviator stress, axial stress minus confinement. In this case, there's no confinement. It's in pascals. This is axial strain, and you see it's the negative of axial strain because I define strain, positive strain is pulling apart. This thing is the beginning of the test. At the beginning of the test, we have to first push the platens together to a certain small stress to begin with. And then we can start the test and we can reset everything to 0. That's what you would do in the lab too. You don't have the platens not touching and have them slam into the specimen. You slowly apply a tiny bit of stress and then you start doing all your measurements. So that's what it's doing here as well. And that's a parameter. And at this point, you can see the stress strain curve. Something must be happening. Let's turn off that. Let's turn on the curve. Oh boy, these are breakages. We're seeing cracks forming, right? Here's the number of cracks versus strain. You're getting more cracks, 16 cracks. You can see it's starting to crack more and more. These are red. These are all tensile failure cracks. And it's still able to build up more load. And now, uh-oh, now it's failing. Now it's forming a continuous thing across there. It's done. Stress strain curve. It's beginning to fail. Again, I stopped it at 80% of the post peak. Maybe in this test, all I wanted was to try to get that peak. Okay, there's cracking. It's all tensile cracking. Basically, it cracks beforehand. There's distributed cracking, and then it reaches a critical state. It cracks like crazy as it starts to fail. That's how these systems are behaving. We've also got a plot here of this is radial strain versus axial strain. If you recall, the slope of this is Poisson ratio. Here's deviatoric stress versus axial strain. The slope of this is Young's modulus, right? And there's a few other ones that might be of interest here. This is actually volumetric strain versus axial strain. Here's a fun one. This is actually porosity in that system. And you can see the porosity is getting a little bit smaller as we keep applying strain because we're squeezing it. Not much, hardly affecting it at all because it's already densely packed, but it is getting smaller. And now porosity is getting bigger as it's failing. Okay. And the last thing, it makes two save files right here. PFC material compression test 0 and compression test 1. 0, that's the beginning of the test. It's ready to go. It's applied the whatever we told it as the initial seating stress. It's ready to go. Everything gets reset to 0. This is so far the stress strain it applied. We were trying to get 0.1 MPa. And so it had to squeeze it a little bit till it reached the value we wanted. Then we ran the test. And that's why then you see over here, it resets the strains to 0. The stress doesn't change. It just is a way of measuring. It resets the strains to 0. And now this is the typical curve you see. When people give you lab data, they don't usually talk about, they don't show you that. That's like the beginning of the test. They have to get the thing set up. Okay. So this is how it works. And so you have this built-in ability to like track these cracks and stuff. This is a very useful thing, right? If you recall when we screwed around with that thing and tried to like put in contact bonds and stuff, we didn't have any good way of seeing the damage. So this has what we basically some fish function, we call it a crack tracking package. It's just all described in the memo, which is going to track these things as histories and allow you to visualize them. Okay. Any questions? Make sense?
Yeah, it's clear.
Yes.
Excellent. Now, let's actually look at, so you can see it runs fast. These are simple models. They run fast. So what I did is I took that whole directory, I copied it, I did the run all, which means every one of these guys got run. So in the parallel bonded one, see it ran it, it made the save files. In the compression test one, it did the compression test. So for example, this should be the same thing as what we just ran there manually. I'm just going to look at it. Sure it is. Look at the compression test cell plot. These are the save files. This is the one, that's the original specimen. Step 1071. Here's the specimen after it got seated. Step 3, do some steps to squeeze it to get to that stress. And then this is the specimen at the end of the test. Now it's up to 59,000 cycles. Okay. And so, of course, you see, I think now the idea right there, that's your plot, right? You can just sit there and throw this into whatever you want to do. Fred, there's my PNG. And here's my, switch this thing. Just a second. If I have a PowerPoint going. All right, just the last time is to make this clear again. There you go. We ran this parallel bond, compression test. We just made a plot called Fred. There's your stress strain curve, right? And we can go from there. So for example, and we're not going to have time to do this, but you get the idea. We did the tension test. So let's actually pull that up. So file, open. We're going to go to the directory where the tension test is. That was already run. It has a project, so I'm going to open the tension test project. And now I have save files. That's the end of the tension test. That's what it looks like. Turn off the displacements. It's beginning to crack. The stress strain curve looks like this. 19,984. So I made a snap of that. I pulled her in here. 19,984. This is that one, right? And no, it's all nice and clean because it tells you everything. It says direct tension test. Okay. And so then I started screwing around, made the red lines, right? The slope, ET prime, stress, strain, pull it off of there. There you go, 1.5 GPa. Why is there a prime? Who knows? Why am I putting a prime there? Anybody remember? Remember, this is a 2D test. And so we're actually squeezing unit thickness rods together. And we're trying to interpret the force displacement response in terms of stress and strain. And there is no direct mapping between a bunch of rods and a 3D continuum. And so that's what this is. And this is talked about in detail in the memo. But we still typically do this. And these numbers are very similar in 2D and 3D. So we ran this thing. And there we go. We got two things off of this test. We got the tensile modulus and we got the tensile strength. Okay, with me?
Yes.
Okay.
Yes.
Then we went, sorry, I got a lot of stuff on here because I didn't take a huge amount of time to go step by step. Then we went here. This was the UCS test that was run. So again, I could pull it up and this is what we just looked at. This is the stress strain curve. I made a snap. I took a line. There we go. This now is the compressive modulus. Again, it's a 2D thing, so I'm going to put the prime there. Stress over strain. Here we go, 2.5 GPa. Here's the UCS value. 2.3 pascals, e to the 6th. That's megapascals, right? Notice that weird little bump. That's because one of the parameters was the initial stress in the axial direction that I want to start with to begin the test. And so that was, I set that here to 100 e to the 3, 100 kilopascals, really small. Okay. And so here we go. We got the UCS. And then if we plot the radial strain versus axial strain early in the process, before it starts going crazy and failing, early in it, it's pretty much linear. And that's my Poisson ratio, right? Okay. And so now let's just do one thing and see what happens. So what are we trying to get? Let's see. I don't remember. Right there. So we're trying to get a compressive modulus of 2.9 GPa. And what did we get? This is the example. So the example is 2.5 GPa. And so we would say, well, what is the key parameter that affects that? So that's the effective modulus. And we have two effective moduluses. We have one for the surface springs and one for the cement. The cement ones have a bar. So as a starting point in this thing, we're just going to set them equal to each other. And if we do, we get this. If we do, and in this data file, we set them equal to each other and they were both 1.5. And notice when we they're both 1.5. So both springs are 1.5. When you do a tension test, the surface springs are not doing anything because they're not touching. It's pulling it apart. So therefore, you're only measuring the modulus of the cement. And look at that. You're even getting macro, the same thing, 1.5 GPa. That's what you set. But now when you squeeze it, you're also adding stiffness from the cement because those are from the surfaces. And so now you should get, if everything was perfectly lined up, that would be the sum of these. It would be 3 GPa. But because it's a packing arbitrarily, it's just close. So then we could go and we could run this again, and we would now jack this up. So I would take the ratio. The target is 3. I'd say 3 over 2.5 and multiply that by this. And then I'd have whatever, 1.8. Then I'd run it again. And I should get really close to what I want. Okay. And let's just do one thing. Let's actually do an even easier thing that'll go faster. So let's pretend we did that and we're happy because we are pretty close. Okay, tensile strength. Let's just do that. Let's match tensile strength. So we measured 0.5 MPa and the goal is 1 MPa. So what's the parameter that's going to affect tensile strength? And that should be the microtensile strength. And so let's actually do that. So shut everything down. So here's how I would do it. Parallel bond, 2D. This is where everything is. Tensile test, that's the base one. I'm going to just copy it. Basically, each project should be in its own directory. I'm going to rename it. So I'm going to call this tensile test, take 1. Go in there. Get rid of the plot. Get rid of the save files. Get rid of the log file. There we go. Fire this up. Change the parameter. Run it again. So let's do it. Here it comes. So we want to, okay, hold on. This test is going to go one level above, and it's going to suck up that save file. Well, that's the material we built. So we can't do the test yet. We have to build a new material that has a different micro property. So I didn't want to do that. So let's get rid of this tensile test, take 1. We got to go up a level. So now that's the parallel bond. Everything's in there. I'm going to paste that. I'm going to rename that. Let's do this, dash take 1. So now, again, let's get rid of the save files. Let's get rid of these log files. And there you go. That's a basic thing. Let's do the material genesis. We'll keep everything else the same. And we're just going to change the microtensile strength. We're also going to go and we're going to change this, the name of this thing. So I'm just going to call this the take 1. That's going to be the name of the material, take 1. Because then when those plots come up, it's going to say material take 1. So when I make those snaps and throw it in my PowerPoint, I'm going to always know what I'm doing here. So here is the tensile strength. And this is set up. It's actually going to give you a distribution, a uniform distribution of micro strengths. And that's the mean, and that's the standard deviation. And so if the standard deviation is 0, that means they're all the same. So instead of doing 1, we got to double it, right? Because we're trying to double the value. So I'll make it 2 MPa. And we're done. We're just going to run the whole thing. So we're going to run this thing, material genesis. And that data file is set up. It had to exit, so it's done. There's my save files. Now let's run the tensile test. Again, let's not, just to be clean. If we left those in there, that'd be fine. It would just overwrite them. So now so again, I'm in that lower level directory. It's going to restore the upper level guy and do the test. So I don't got to change any parameters for my test. I just am going to look at what's happening. Now it's loading it. Get rid of that. Look at the stress strain curve. We're trying to get 1. Oh, look. Let's see if we make it. So we should have 10 e to the 5. This should reach 10 before it fails. Last time it failed at 5. So it's stronger so far. I don't think there's any cracks. Nope. So far, so good. And since we doubled the micro strength, in this case, there should be almost a linear relationship. And come on, fail, buddy. Boom. Again, it was that exit was in that file, so it shut down. I'll just start it up again and look at those save files. And so there's my stress, there's my specimen. There's nothing here. I got to double click on the save file. So this is at the beginning of the test, T0. This is at the end of the test. And there's those little cracks in there. Here's the stress strain curve. And there we go. So we got like about 11. We got like 1.1 about instead of 1, but we're quite close. Okay. So that's the process of using this material modeling support package. Okay. So essentially, it's got this built-in scheme for making a packing in a controlled way, and then for doing these different tests, and everything is parameterized. So, I like to say there's guys I've set this up for, like at oil companies, like they don't know really anything about PFC. You really don't need to know anything about PFC to work with this, except you need to understand how to manipulate data files and set parameters and, do plotting and things. But, you're not writing any scripts, right? You're just changing values of parameters. Okay. So that's what I'm going to say about calibration and about using this package. Okay. Are we good? Make sense?
Yes.
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 Okay. Excellent. And I can tell you, tons of people have used this package over the years. Most journal papers where people do stuff with PFC are, they're plots out of this. And this is what you should do. And of course, what's also, because you guys now know fish, or at least you know enough fish to be dangerous, and you could learn it if you needed to. These are all just data files and fish functions. So you could go in here if you needed to, and even use that whole thing as a starting point, and then maybe modify things a little bit here and there to write your own stuff. Okay. So that's that. Now, 2 things. I want to just do a quick high-level, relatively short description of other microstructural models, and then take a break, and then we're going to talk about the subspring network guy. So I'm going to fire up my PFC lectures. By the way, I've been developing this course as we go. So what I'm going to do when we're done here is give me like a week or so, and I'm going to clean all this stuff up so it's a nice coherent set of things. And then it'll all fit together. Okay. As you can see, I've just been adding things in an ad hoc fashion to this one file. So other microstructural models. Here we go. Bonded particle models. So let's start here. This is what we've been talking about, right? And I need to define these things clearly. What is a bonded particle model? I'm going to say that it's a packed assembly. So it's a packed, but it's not necessarily perfectly interlocked, right? All these disks and stuff, they're packed. There's all kinds of, they don't perfectly fit together. So it's a packed assembly of what? Particles. They're unbreakable. Everything we've done here in the world of PFC, these by default in PFC, particles are rigid. They're rigid, they don't deform, and they also don't break. Okay? And so it's an assembly of packed, rigid, unbreakable particles. And what are those particles? They're the things in PFC. They're either spheres, or they're clumps, or they can be rigid blocks, which are polyhedra, right? And then I'm going to say the particles are, you got packed particles and they're bonded. And so that means they have bonds at the places where they're touching. And furthermore, I'm going to say, okay, and they're modeled with, they're typically modeled with the PFC codes, right? And so an example of that is, here's a big cool thing where what this person did, this is a researcher in China. Do I have his paper? Oh, come on. Let's see if we're lucky. It should all be here. He wrote this journal paper. It was really fun. I saw him at a conference. He's like, look at this. I did this cool stuff with your model. So he did a grain-based model of a certain type of granite. Okay. And let's recall what a grain-based model is. He started with a dense packing of discs to begin with. And then what he did is he somehow generated a perfectly interlocked grain structure, which is shown here. And I'm not sure how he did this, okay, but somehow he did. And then he overlaid that on top of the collection of discs. And the discs are smaller than the smallest grain here. And so that then he managed to do by having a certain contact model inside. Those are two particles of the same color that represent a grain. They have a certain contact property and contact model. And then he used this smooth joint contact model for the contacts along the edges at the boundaries. And so, and in this case, the material inside here is a flat jointed material. It's not a parallel bonded material, right? And again, so here's what I'm saying. In this type of a system, the grains are these bonded discs using flat joints. And so because it's a grain-based model now, the grains, the particles are discs. The particles are unbreakable, but the grains now are defined at a higher level. And because they're bonded discs, they can break internally, so therefore the grains can break. So his grains are bonded discs that can begin to break, and the boundaries are using that smooth joint contact. And the smooth joint contact is going to basically make those boundary contacts dance as if the two surfaces were aligned with the joint. And that system starts out as being bonded, and then it has a concept of breakage, and after it breaks, it's frictional. And Bowen knows all about that kind of stuff. Just want to make sure you're still out there, Bowen. Hey,
Yeah.
because
Yeah.
Bowen is taking this and adding time-dependent the damage to this thing. You may recall he gave a nice little talk some weeks ago. So this is the bonded particle model. Now you're going to see when we look at the other two models, we're going to also talk about how are the grains modeled in the other one? How are the boundaries modeled in the other one? So what we're starting with this, because this is the one that you have in your head that we've been discussing in this course. And this is now a typical specimen at the end of a UCS test. So at this point, it's already, the stress strain curve is drastically in the post-peak region. And you can see here, these are basically using the crack tracking scheme, and these are broken bonds. If we zoom in here, it's not the perfect picture, but you can get the idea, right? So you can see, and he's coloring it green, means that it's on the boundary between two grains. So those are the smooth joint contacts that are broken. And then I think he's using blue and red for internal to a grain. And so here you've got this, very sophisticated, you've got all the fundamental behaviors here of rock as it's failing. Now you have grains, and these grains not only can break, but they're deformable. Because all of these guys have springs, right? So that whole system inside there is deformable, and it can break. So you've got deformable grains that can break, and after they break, the interfaces become frictional. Remember, after this thing breaks in here, there's also now, he's saying, okay, if a new contact forms, it's just a linear contact model with friction, right? And then the same thing on these interfaces, they can break, and after that, they're linear, they're frictional, okay? So this is a system, and then he does all kinds of interesting studies and stuff with it. So that's our starting point, bonded particle models. So if we go back to 1998, Peter Kundal and I had just recently, we were in the process of developing this bonded particle stuff, and we had a little workshop at in Seattle called Microstructural Modeling of Rock Fracture. And, you know, it wasn't quite as at the point of having smooth joints and all this other stuff. We just had really simple contact bonded materials, but everybody was super excited because this was a new thing. And we were looking at it. Now, since then, we've moved forward, and there are slight variants of bonded particle models. And even as you're going to see, a whole different approach that can build microstructural models. So what are those? Let's first just do the slight variant, which is this one, bonded block models. Now, what's a bonded block model? First thing, perfectly interlocked mesh. Remember, the bonded particle model doesn't necessarily have to be interlocked. This is somehow magically making a mesh, and it's going to use the mesh, it's going to use the elements of the mesh to be particles. So we're not going to call them particles, we're going to call them blocks. And blocks are going to be polyhedrons. And those polyhedrons are either going to be tetrahedrons or Voronoi cells. And we'll talk more about that later, but that's a way of discretizing space into interlocking polyhedra. And so now you have a perfectly connected set of blocks, and the block itself is unbreakable, but it's deformable. So it's not rigid. So it's deformable, and in addition, it's not just linear elastic. It could have any constitutive model. And so it has, in these cases, people typically might use an elastoplastic. So now just a single block inside of itself, this one's for AAT, is behaving like a continuum. So now we've gone from Newton, which only knew about rigid things, and we've gone to all the way down to having an idea of a continuum elastoplastic material with a general constitutive model. Pretty cool. It's still got the word bonded in it because you have these perfectly connected polyhedral blocks, and they're bonds at the interfaces. Because it's a polyhedra, every interface is a polygon, and every interface is two guys, two blocks. So that's why I can say block-block interface. And these things are typically modeled with these other codes, UDEC and 3DEC. UDEC is a two-dimensional code, 3DEC is a three-dimensional code. By the way, these were the codes that originally began as Peter Kundal's research that he was doing pretty much at the same time as PFC, because it's easier to do the discs and glue and take them. And he did discs that were granular material that could move, wrote the famous paper in 1979. And then around that same time, he also generalized the idea and said, I could actually make it, they don't have to be discs or spheres, they can be polyhedra. And so, and then he said, well, it's a distinct element code that does these polyhedra. And this was back then in the old days, it was the first one ever, so it was pretty cool. So we called it the universal distinct element code. Could do everything. Completely universal. And of course, you know, no, it was only a 2D. But then, of course, he then went and said, well, let's make it 3D. So then he put a 3 for a three-dimensional discrete element code. I mean, ideally, this should have been 2DEC, but it was a pretty big deal. So we called it universal. And then it's like, oh, yeah, well, actually, it's only 2D, so we'll call it 3DEC. And these two codes still exist and are sold by Itasca. So what do these look like? So here's an example. Let's unpack this one first. This is a 3D model. This is using 3DEC. And this is a tunnel. This is a circular tunnel in a big, huge rock mass deep underground. And it's a granite. And this tunnel now is beginning to fail in the roof and in the floor and a little bit in the sidewalls. This is loaded with like 60 MPa horizontal load and like 10 MPa vertical load. And if you load a borehole or an opening like that, you're mostly squeezing it, so you get really high compression above and below, and it ends up causing this localized damage. Many people call this a notch. And so the only thing we're seeing in this model is the blocks that have completely broken free from all surrounding blocks. We call those fragments. So this yellow guy, all of its polyhedral interfaces have broken, okay? And this is just looking at it from the side. And so this has localized now into this damage above and below this notch. And there's also some tensile failure in the walls. This is quite realistic. This is matching the behavior of a certain thing called a mine by experiment. So that's a bonded block model in 3D. This is the bonded block model in 2D. And so you see right here, these are the grains now. Now the grain is a block. That's a single discrete element block right there. And then to make it even more exciting, this guy then went, so instead of having an elastoplastic constitutive model, he just has a linear elastic constitutive model, but he broke the block into sub-blocks. So these triangles, so that one block is now 6 blocks, and the blocks are triangles. And the triangles inside of a grain, now you can think of this as a grain, and he's got discretization inside of it, and now it's breaking on the interfaces. So these are triangles that are linear elastic with interfaces that can break. So that's what he's got, elastic triangular blocks, and you can have breakage along these interfaces, okay? And after they break, they're frictional, okay? So this is basically taking a bonded block model and overlaying a grain structure sort of like on this thing. And then you get all these cool things. This is a UCS test, and you can see now thing is opening and things. So now this is different than the grain-based model with the BPM. In that sucker, you had a huge number of little guys glued together. Here, you have these blocks. You have much less freedom for that thing to fail. But it's also much easier to see the failure because it's this well-defined opening. In this guy, it's kind of a mess here. You got all this like connected little stuff. Which one's more real? I don't know. They're both models. Going to be useful for some things and not for others. So this is the world of bonded block models. There's a lot of work that's been done out there for bonded block models. Just one note, there's something people talk about called a synthetic rock mass. You'll see that in the literature as well. And basically that's a term that's often applied to bonded block models. The idea being that what you're doing is you're building a rock mass, because with these models, in these codes, UDEC and 3DEC, you can start with a packed block assembly and you can do cuts in the code. So you say, make a cut. And what that will do is cut the blocks into smaller blocks. And so when you're representing like at a rock mass scale, like adding this tunnel, this is 3.5 meter diameter. There are bigger joints typically. So you can build a bonded block model like this, and then you can cut in all these joints. So people often are doing that. So we think of that as a rock mass scale thing. So my friend and colleague Matt Pierce many years ago came up with that term, synthetic rock mass. In fact, I remember sitting in his office, spending a reasonable amount of time talking about what should we name this thing. And he came up with the idea of calling it a synthetic rock mass. And those models are often used again at that bigger scale. They're at the excavation scale, and they're looking at rock mass properties. If you did a giant UCS test at the scale of a meter by a meter by a meter in the real rock, it would be weaker than if you did a UCS test at the scale of a 50 millimeter sample. usually, because most rock at a bigger scale is going to have more initial damage in it. So it's going to end up being weaker at a larger scale. So we talk about rock mass materials. They're less strong, they're less deformable, things like that. Okay, now here's this other cool thing. This is something that came out of the finite element world. And so for those of you that don't know, if we go all the way back to 1960, there are people at aircraft companies who wanted to try to better model the structural. There were structural engineers who had to build airplanes. And the way that they had to do their structural analysis was mostly by hand calculations. They were just beginning to be computers in 1960. And so people developed a technology that allowed them to solve structural mechanics continuum problems using computers. And that method is called the finite element method. And what they do is they discretize the body into a mesh of what they call elements. And those elements perfectly fit together, and those elements have a constitutive model, and so they end up behaving. Those elements are not grains, they're not particles. It's just a way of discretizing a continuum. And so it's called the finite element method. And those things, that was developed in about 1960. And since that time, it's become a universal method for doing much more than just structural mechanics. It still, though, is used for structural mechanics massively everywhere. All the mechanical engineers use it. All the structural engineers use it. I don't know what the number is, but I would say the vast majority of structural mechanics codes are finite element based. Abacus is one of them. Big, huge company makes these finite element codes. Started out way back then, still exists. And so there was this, most people doing structural mechanics in the early 80s were in the world of finite elements. One of these guys named Mungiza came up with this idea for his PhD and said, well, gosh, these discrete element things that Kundal is starting to do, this is early 1980s, they're pretty cool because they can break apart and they're like blocks. They're blocky systems. He said, could I make a finite element code dance as though it was a blocky system? And he came up with this thing called the hybrid finite discrete element. So it's the hybrid finite element and discrete element. And what he does is he says, well, let's just start with a finite element code. And let's, at all of the, just look in here, just first look in here in one of these guys, the green guys. Pretend you're only seeing the green thing, nothing else. This green thing is a finite element mesh of triangles that perfectly fits together. It's a mesh. It's not grains. It's a mesh. Now, you start with that. And then he said, well, on top of that mesh, internal to the mesh, let's put a special finite element that has zero thickness that's just going to live at the interface between two mesh elements. And that little interface element is going to give us a traction law. It's going to say, what is the force displacement? So it's a traction, it's an interface. If you pull it apart, it's going to have a certain force displacement relationship in the normal direction. It'll eventually be able to break. If you move it in shear, it'll have a different force displacement. It'll eventually break. You can get those force displacement relations by doing fracture mechanics analysis of an interface between two bodies. And he put that in then. And so now he's got a finite element code that has the ability to break along the boundaries of the elements. Okay. So that's kind of cool, which means you start loading this and it starts to break, but you have to then stop the analysis because as soon as it starts to break, now the mesh, what the heck do you do? Now you got these surfaces and the finite elements need to have a mesh where everything fits together. They're a continuum. And so he said, oh, but this is cool. What if we go And now, if one of these little triangle guys gets breaking on all sides, let's actually turn it into a discrete element. And so let's have the machinery of a discrete element code. What does that mean? That means it can have these particles that can move around and can come into contact again and form contacts and have forces. And so he basically wrote a specialized finite element code that was extended to also behave. So it starts out as a finite element, and as it starts to break, those things become discrete elements. So you can start having new contacts form and stuff like that. So that's what this thing is, okay? Now, this is a very sophisticated, much more recent 2020 thing where you take that as the basis and you lay on top of it at a higher level a concept of grains. So again, we would call this a grain-based model. So somehow they generated this network of perfectly interlocking things. These are not Voronoi tessellations. They're not polyhedra. Don't know exactly how they got this discretization. And they lay that, and they start with the grains, and then they create a finite element mesh that perfectly fits together of triangles that respect the boundaries of the grains. And then they give properties at these interfaces, which are supposed to be the properties of the boundary of a grain. And then they give different properties inside. And typically, the inside world is usually linear elastic, isotropic. There now is the ability, there's a code called Geomechanica is a company. They make a code called Irazu that you can buy. And they've recently added the ability to have elastoplastic constitutive models in here. And so that code this system is basically behaving a heck of a lot like a bonded block model with 3-dec, because you got a polyhedral thing and it has a general constitutive model. And the 3-dec one is only a constitutive model. It doesn't break. This guy here, that can also break. Okay, so here's a fracture that's formed. It has to follow the boundaries of these triangles. Okay, and they do this in both 2D and 3D. Okay, instead of triangles in 3D, they're tetrahedrons. And there's all kinds of what they call mesh generators that exist nowadays to generate finite element meshes of tetrahedrons. And nowadays, those meshes are used for all sorts of other things too, like visualizing Steven Spielberg movies when things are breaking and flying out in the screen and all kinds of stuff. They use these meshes to do all kinds of things to represent 3D bodies. So there's mesh generators out there. And this then is that type of model. Again, UCS test in the post-peak region. And you can see how it's forming gaps here. These are, you could think of as fractures, right? This is like axial splitting. Okay. And some of them are actually going through the grains. Here's an example. It's going through the grains. Okay. So this would be a way of creating essentially a grain-based model instead of using this approach, right? So it's different in detail. At the higher level, it's pretty similar. As these computational techniques become more and more sophisticated, they kind of merge together in some sense. Okay. So, and I would say that nowadays, 15 years ago, this was still pretty new, this stuff. And most people who were doing this type of modeling were using either PFC or UDEC 3-dec. Now, many of the research papers are using FDEM. Okay. Shihang, would you agree with that?
Yeah, the FDEM is popular right now. Do you remember the Christina?
I'm sorry, what?
The postdoc when you come to China last year.
Okay.
Her name is the Christina. If
Christina,
I spell
okay.
it right. Yeah, and she she's now a professor in Wuhan University, which and her boss Wu Zhijun works with FDAM so much, and some of students in their group do stuffs with FDAMs. So it's really popular in China or in their group. So I know this well.
Got it. Yep. So yeah, so just at the bigger picture, if you start looking into this world of microstructural models, and have I missed any kind of fundamental ones, Shihang, here?
Fundamental ones?
Like other kind of microstructural models. There's a huge number of, variants of these things. But is there another big one? Big technique that is not listed here?
I think it, no, as far as I know. I think the microstructure is basically these three models.
Yeah, the microstructure, because there's also a lot of people, they only look at things at a bigger scale than this. And there are a number of different types, kind of like discrete elements, but using different schemes, smooth particle hydrodynamics, crazy stuff like that. That they're doing things kind of like this as well. But in the world of rock mechanics, as far as I know, when you're actually trying to build a microstructure of a system, these are the most common ones. Okay. That's what I'm going to say. We're going to take a break. Are there any questions? Get the idea? Oh, the last story. There's got to always be a story. The story about this is that this technique was developed by Professor Munjiza, and I'm pretty sure it was during his PhD. And then I met him, I don't know, 98, something like that. And he had just recently written a book about this method. And I remember all this because he was very excited. Like, oh, look at this! I wrote this book, this new method. I think it's going to become a big deal. And then he gave me a copy of his book. That was like so long ago when you wrote and like a paper. He gave me copies of his papers because in the old days, when you wrote a paper, nothing was electronic, so you would actually get physical copies, nice high quality copies that look like little books of your paper, and then you would go around at conferences and actually give people your paper. So I remember getting some of the early stuff of this. So, okay, let's take a break. Let's continue. So, we're going to close her out with the latest and greatest model for rock, for granitic rock. And what you have are some links here. We're going to go through the talk. There's also a full-blown proper journal paper that describes all this work, and there is, just like for the material modeling support package, there is a whole full-blown modeling package that you can use as a starting point to do all of this stuff. Okay, I'm hoping that this work will be moved forward by others, potentially Yongqing. So, talk, here we go. So Shihang, you've already seen this talk, but I'm thinking it might make a lot more sense to you now after all this background. So this is this crazy thing. We'll try to unpack what this all means. First of all, it's a full 3D model. A lot of these microstructural models that are out there are only in 2D, and they're cool and they're useful, but they're definitely limited. There's mechanisms that you don't get in a 2D model, and as we've talked about, there are often these weird things of like rods. This is a 3D model. It's made out of Voronoi blocks. There's why the word Voronoi is in there. They're breakable Voronoi blocks. And then the internal detail is they're joined by magic springs. And that's a contact model called the subspring network. So let's unpack all that. And then we're going to talk about how this model has been shown to reproduce the fundamental mechanisms that occur at the scale of a laboratory specimen of rock, of a granitic rock, okay? So you could say that we've had these 15, all these 15 lectures to get you up to the point where we can talk about this, okay? A little bit of a bigger background first. This is part of the reason why this model even exists. It's been motivated by this idea of putting radioactive waste deep in the ground. And there's a company in Sweden. It's a government-run company whose job is to manage all the waste from their nuclear power plants. And the way they do that is the waste is in the form of these fuel pellets. These things, you can hold them in your hand. They're really small. That's probably like 4, 7, 10 millimeter, 12 millimeter across. Those are the uranium that's been used to heat the water to make the power. And now these things are radioactive. So they put them in a big tube, and then they put a bunch of tubes together. Then they put all these tubes together and put even more of them together into a big canister, copper canister. You can see the length scale there, 10 meters. They seal that thing, and then they go deep underground, and they make holes in the floor. They make the holes bigger than the diameter of this. They stuff in bentonite clay between the gap. The bentonite clay is in there because when this gets wet, the bentonite clay swells, and it helps to take this hole and apply confinement to the surface of the hole. And as we've discussed, rock gets stronger when it's confined. And then these big drifts, what happened there? I heard a beep. I don't know. Then these big drifts get filled with backfill, and you're all done. You go back up to the surface, and then hopefully you monitor this for a long, long time. That's the plan. Oh, here we go. 500 meters down. And this is actually all been designed, and they're beginning to do the construction of this thing right now. And as they do the construction, they're going to be doing tests along the way to confirm the modeling assumptions they made along the way. The issue for this aspect of it is that this radioactive material is hot. It's going to be about, what's the number? 100, 200 Celsius. It's quite hot. And it's going to be hot for about 200 years. Then it'll start to declare. And so, of course, since it's hot, it makes the rock expand. It can make the rock break. And you can get this thing called spalling, where it's localized breakage. This is looking down one of those deposition holes. And you can see this localized breakage on the surface. And this could be bad because it could provide pathways for water to go through, and then eventually the water gets radioactive and it makes its way into aquifers. And so the goal here is to have a grain scale model so we can better understand this process. Okay. And this is, for example, in a hard rock, and this stuff is hard rock. This asphodierite is a lot like lactobonite granite. This is a test on lactobonite granite. You can scale 1 millimeter, and it's loaded similar to this, and you get a breakout notch. And you can see this is complicated, and you get buckling of slabs, and you get breakage of grains. So this is a complicated phenomenon. So we want to try to match that response at the laboratory scale. So this is a specimen of pink lactobonite granite, and we want to match its lab scale response. That's where we're at now. And then we'd like to apply this so that we can actually match the field scale response, which is that spalling that you saw. And this is spalling that's been done in a very careful environment in this thing called the Mine by experiment. It's a bigger thing, 3.5 meters, and they get this notch that forms in the roof and the floor. Okay. We really don't know how to do this very well. There's been some work by Professor Rasmussen in Brazil to upscale this, and it seems to be very promising. So we're talking about the first step, lab scale response. And this SNBV model gets excellent lab scale response. And the reason is because we have the mechanisms that are occurring at the grain scale. And we're going to talk about those. And we're going to show how the model mimics those different mechanisms. And for each mechanism, if a model's going to mimic it, there has to be a few parameters. So the more mechanisms, the more parameters there's going to be. This upscaling is still an issue in this whole world of modeling this type of thing. We call that upscaling. There's all kinds of ways people do it. They're still relatively ad hoc. So here's the, going into this, we're guided by the microstructure. There's granite. We've seen this before. We've talked about these things, complicated grains. So what we're going to do is build a material that also has interlocked grains. And these are polyhedra. They perfectly fit together, and they're definitely simple. Notice the granite is complex shape. This one is simple shape, but it's a step in that direction. Okay. So this is a relatively new, you can see 2022. This is by Professor Rasmussen in Brazil. Great guy. He's one of the few people in the world who's as enthusiastic about things as me. You should see when we get together in some office with a whiteboard. It gets a little dangerous. It's so fun. He came up with this idea of combining two things. So that's the word hybrid. Combining what we've been talking about, discrete element model, but this time with something called a lattice model. And a lattice model is basically, people have been doing this for the last 20, 30 years, where they basically just make a network of springs, complicated network of springs, and that's called a lattice. And if you make a complicated network of springs and you allow the springs to break, it's a lot like rock. It's not a full discrete element method, though, the lattice, because once it breaks, the spring is gone and it doesn't have contact detection. So it's not like you actually have a surface that can come back into touching. But if it's a small strain thing, you start with a whole bunch of springs and they all start breaking just a little bit. And like the spalling, it's just a little bit of breakage, might be good enough if you don't need to move the simulation forward when you have fragments and all that stuff. Okay. So Leandro Rasmussen did this excellent work, published it in a number of papers, and then we said, oh, geez, could we do that with PFC? And we're going to also add grain breakage to that. And so, and Rasmussen also had some grain breakage. The question, basically the idea was, could we put this in PFC3D? And so that required the work of my colleague, Matt Provence, and he built a special contact model that he calls the subspring network contact model. And, oh, what did Rasmussen do? Rasmussen combined the lattice with a discrete element. What does that mean? The lattice, remember I said it's like a collection of springs. These are not lined up. These are arbitrarily connected. And how are they arbitrarily connected? Oh, they start with a Voronoi tessellation and put springs at all these interfaces. But they just have the springs that can break. Well, Leandro said, well, geez, let's combine that with it. Let's just make a discrete element model with the Voronoi cells as the blocks, as the particles, and then at the contacts, make it a lattice that can break. But now after it breaks, it's a full-blown interlocked set of blocks. That's what this scheme is, okay? This is the work that Leandro had done and published, and he did I call it a pseudo 3D model. He basically, it's a 3D model, but the only thing he did was look at these certain thickness polyhedral cylinders, okay? And he got excellent response. So the question that we explored with this research was, could we not only do it in PFC3D, but do it in proper 3D? So our model looks like this, okay? So what's the basic idea? You start with a collection now of rigid blocks, and you know what that is now. Those are polyhedra that can push against each other. And remember, PFC3D has nothing to do with Voronoi tessellation. You could just make a bunch of those and throw them in a box, and they'd bounce around and do whatever they need to do. That's a fundamental particle in PFC. In this case, we start with a Voronoi tessellation, and we replace each Voronoi cell with a rigid block. So now we have this starting point of perfectly interlocked rigid blocks. And each contact then is between two rigid blocks. And each contact is a polygon. So what do? We make a simplification. This is an example of a polygon, the gold guy. We're going to model that as a disk. This has the same area as the polygon. And in addition, there's going to be a subcontact here. So these are like, this is like a flat joint model. Each of these subcontacts is like an independent little subcontact model, and it can break and be frictional. But the overall behavior of this contact, because there's only one contact at this interface, is the result of these three guys acting together. So it can like partially break. This guy can break and those guys hang out, okay? And each one of these guys carries a force and moment. It can break, it's frictional, so you can have this partial damage at the macro scale, okay? This is what these things look like. There's my Voronoi tessellation. This is all in PFC3D. Remember, the rigid blocks have these rounded corners, rounded edges. Every one of them has the little blue guy, which is this interface. Here's what it looks like in that microstructural box. Okay, all of these plots, all this stuff can be done with that modeling package. Now, remember we talked about every structural model like this has two types of things. It has deformability and it has strength. So the deformability, in this model, there's three parameters. You're actually putting in what we call the contact modulus, and you're putting in a contact Poisson ratio. So every single contact, you have to give it a value of these three things. And what's this? We're typically going to give a Weibel distribution. That's a particular type of distribution, statistical distribution. And it's well defined mathematically. It's used for all sorts of things. And it's controlled, the width of the distribution is controlled by this thing called the shape factor. If you set this to infinity, everybody's the same. Okay, so these are the parameters. So what the heck is this one? Here's what we're going to do. Now this is a contact, normal PFC contact. Now that contact has 6 degrees of freedom. It can resist translation, which is 3 degrees of freedom. And it can also resist moment. It can resist rotation. Rotation produces moment. Translation produces force, which means that there's 6 stiffnesses. These are the translational stiffnesses, and we do this in a local system, a normal to the surface, T, that's in the plane of the surface. That's an orthogonal system. 3 values. And rotational stiffnesses. And we have to give values for these things. And so, for example, a bonded block model, these guys would be deformable blocks, discrete element blocks. And in that system, it has the same thing. And you actually have to set these things. You have to set all 6. And we talk about like joint stiffnesses and things. And then people give values for all these. Well, here, you don't set these. Here, you use what I call the magic formula. And this formula really only has one material parameter, which is this contact modulus. Look at this, EC. What's A? That's the area of the cross section. That's the polygon. H is the distance between, what is it the distance between? It's the distance from the, it's the distance between centers of these cells, right there, H. And then here, these are integrated properties of the cross section. Moment of inertia about the X and Y, or about the S and the T. And this is rotational, what the heck is that called? Polar moment of inertia. The key element is for every single contact, there's a polygon. And for every single polygon, we know all of these things. And so the only parameter then you give is this EC. Okay. Now here's the cool thing. If you give every single contact the same value of EC, when you squeeze the overall assembly, like you do a UCS test and you get the slope is the macroscopic E. And if you give all these guys the same value, EC, then that macro modulus will equal that. Okay. Which means if you want to match an overall macro modulus, you just set that to be the contact modulus everywhere. It's the lattice equations end up producing this response. But also, they have a 0 Poisson ratio. So if you make this assembly, you set this to all be the same. When you squeeze it, it doesn't bulge out. It's kind of crazy. Essentially, all the force chains go straight down. Okay. Well, that's been dealt with by doing something called adding another parameter called the contact Poisson ratio. And there's a scheme that was developed that's called the fictitious stress approach. And essentially, it takes the value of contact Poisson ratio and does a certain thing to the model so that now if you make all these the same, the macro value will equal to what you did it. And this fictitious stress thing is it basically looks every time step at every single contact, and it looks at the forces, and it basically says, if I wanted this to deform with a certain Poisson ratio, I could back calculate what is the additional force I would need to apply to make it do that. And that's why they call it a fictitious stress approach. So it's going in there and adding all these little tiny forces so that the overall deformation has the Poisson ratio you want. Okay, so this is pretty cool because if you set these two values, you give two different values, and if you put them the same everywhere at all the contacts, you get that E and nu. Nice. So now you get this linear elastic isotropic response, which is all interesting and cool, but that's the starting point. We want these things to break. So why do they break? They break because tension gets generated. We've talked all about this. This happens in real rock. This happens in these type of microstructural models. Somehow you squeeze and you get tension. In this system, with the doing this approach, if we set the E sub C and nu sub C, if we set them all the same everywhere, a certain value of E sub C everywhere and a certain value of nu sub C everywhere, we don't get a Poisson ratio, okay? And we don't get tension. Forget the Poisson ratio. We don't get tension. In other words, we make them all the same, we squeeze it, we don't generate local tension. It's kind of crazy. But if we start giving now a distribution of those ECs, and this is what we mean by distribution. This is probability density. This is like counting the number of them. So let's say there's 1,000 contacts, and there'd be a bunch of them that have an EC of about 80, and a few of them that have an EC of 40. This is a distribution, and it's controlled by that shape factor, the M. And so if M gets bigger, here M is 3, 5, 10. As M gets bigger, the distribution gets tighter. This is directly related to the tensile forces, those micro tensile forces. So this gives us a way of dialing up or down the induced tension. And it's the induced tension that controls everything. So this now is giving us a way. In all these other bonded models, we didn't have a way of controlling that. We just built a microstructure, gave it values of Kn and Ks, and just, wow, we got tension. Isn't that great? Here, we have a very way of quantifiably dialing that up or down. Okay. And this is just mentioning we couldn't do this in the past. Now we can do this in a controlled fashion. So the idea would be any kind of microstructure. In rock, there's different things that produce that microtension. Now we have a model that allows us to control how much we get. So the idea would be that any kind of real microstructure in principle could perhaps be mapped into the amount of heterogeneity induced tension you get. That would be it's giving us some control over that. Okay. Let's look at the model now in terms of the things that it can do, each of which have parameters. And let's talk about the corresponding actual physical mechanism. So we start with interlocked Voronoi cells, and that is representing the interlocking granite. And then we have parameters. So we just talked about the deformability parameters. That's that contact modulus, contact Poisson ratio, and the spread, the shape factor, spread of the distribution. That allows us to have to generate and control this heterogeneity induced local tension, which is a real fundamental microstructural feature that drives the damage in rock. This model now also has all these interfaces all over the place, and these interfaces have the contact model behavior that they start out as bonded, and these subcontacts can fail, and when they fail, they're frictional. So now you have the cells, each of the Voronoi cells is really like a grain. That grain has deformability, and these interfaces between the grains are bonded and then frictional. And that type of system, right, allows you to have breakage of the between the grains. We call it intergranular damage. And you then have sliding. So there's no breakage of the grains yet. So this is intergranular damage. So it would be like a granite that started breaking at the boundaries, which is how most of the time it breaks. However, at higher load, you also start to break the grains. So this grain breakage in the model is allowing you to have breakage within the grains. And we're going to have a simplified version of that. We're just going to split the grain. If it wants to break, breaks into two. And then we also are going to have the ability to specify an initial fabric of microcracks, gaps and slits.
Oh, well, I guess there's something wrong with the...
And I think I'm back. Am I back?
Yes.
Okay. Microcrack fabric, which is in real rock. And as soon as you put that in your model, you get all of these real behaviors of rock, of granite. You get, when you squeeze it, it starts to get stiffer because you push together those gaps. If you squeeze it a little bit and measure the stress strain curve and unsqueeze it, it doesn't go back to zero because you start getting some sliding. That's called hysteresis. You lose some energy. This business about when you start to load and eventually you start to get cracks forming, that point at which it begins to happen relative to the UCS can be controlled by the microcrack fabric. And having the fabric also means that when you squeeze it, it's stiffer than when you pull it. Okay. These are all things that happen in granite. So now let's talk a little bit about breakage of grains and how that was put in to the model. Let's talk about the real behavior. So first of all, if you do a UCS test on a granite, you typically get this type of behavior. This is, again, stress difference. So it's UCS test. This is axial stress. This is axial strain. This is what you measure. And when you look at this really close, this is 1976. Okay, this is early work. You start first, it's pretty much linear, and then you get a deviation from linearity, and this is when the rock starts bulging out a little bit. This is happening because there is damage in these guys. I'll tell you what they are in a minute. Large aspect ratio cavities. And then as you go even higher, you start getting even more deviation from linearity, and there's even more damage happening. And these are happening because you're getting cracks going across the grains. And also you're getting a lot of cracks interacting. So here is a crack across the grain. See this? There's a fracture here. It hit the grain boundary. It went boom, it split the grain, continued on up over here. Okay. This is the same rock, westerly granite. Okay. These are these larks. This is crazy. Look at this. This is 10 microns. This is inside a grain of the granite. And if you look at this crazy detailed scale, remember a human hair would be 5 times the diameter of this picture. Almost nobody ever looks at rock at that level. If you really do, okay, in this particular granite, there's all these crazy openings, and they call these things large aspect ratio cavities, okay? And in this rock, actually, 30% of all the grain boundaries have these things in them. Super small, but they're there. And these are the guys that start doing nonlinear stuff. They start closing up, doing all kinds of sliding and things like that. Okay. They also, some of these are healed, where like some kind of cementation has happened, but those are weaker points, and they start doing stuff and moving around and failing. And that's why you're getting this. Okay. So this is happening in the real rock. This is just showing for the lactobonate granite, if you load it in this fashion, or you have high sigma 1, low sigma 3, you get these breakout notches, and here again you see all this splitting of grains. So this is saying, look, you really get grain breakage in granite. How do you model it? Okay, well, we're still not at modeling, we're still at trying to understand the physics. So people have taken quartz sand, so right, granite has a lot of quartz crystals that have grown together. So then let's take sand that's made out of quartz and take these grains, here's a grain, and put it between 2 other grains. This guy probably spent weeks of time trying to figure out how to do this and build a machine to do this, but they did. And then they took high-speed photographs and they measured force displacement and all this stuff, and they did it for a huge number of these sand grains. And you can see as the time progresses, you can trace the failure process. You start to load it and you start getting damage above and below where it's touching. That damage then zips through, splitting, and now you're just finishing the process. And now it's even more load. Now this guy's starting to crush, and this guy just blew off, and you're left with this. So this is the typical failure mode of this 2 grains getting pushed together. Okay. Well, remember, this is not granite, because the grains are actually all connected to each other. It's not as simple as this. But this is data. This is what people know. And the key thing here is what they do in this test is they measure force, right? Stress is a made up thing. Stress is a theoretical thing. So they measure force off of their platens, and they get a force displacement curve, and they take the peak value of force because it's brittle. So the force goes up, 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 and then boom. They take that value and they say, well, we're going to have to come up with a stress because we want to express strength in terms of stress. So what are we going to do? Well, we'll take sort of like the equivalent radius that has the same area as the cross section. And if you take that force that I measured in the lab and divide by the area, I'm going to call that a failure stress. Okay. And I'm going to call that the strength. So 2 MPa. But if I do like 100 of these tests, I'm going to get 100 different values. And so I might get 100 MPa, I might get 93 MPa, I might get 87 MPa, and I might get a whole bunch of them that are near 100 and a few that are 87 and a few that are 50. And I get a distribution. Any kind of real strength that's measured in a lab is never always the same. Even for something like a steel bar getting pulled in tension, it's never exactly the same. So if you carefully do this, you get this distribution, and that distribution can actually be fit extremely well using the Weibull function. Okay. So people know this, and what's crazy about it is that that strength follows this Weibull distribution in such a way that what you find, like remember I said there's a bunch that are 100, there's some that are 90, some that are 80. Well, the ones that are 100 are the smaller ones. The smaller ones are stronger. The bigger particles are weaker. Okay. This is what they see. Okay. So bigger particles are weaker. And just a second. Yes, let's just talk about it at this level. Bigger particles are weaker. Why are they weaker? Well, people can postulate that the reason this thing actually finally fails is that there's some kind of critical flaw in here that gets triggered. And if I have a bigger sample, I'm more likely to have a critical flaw. And so I'm going to fail earlier. And so that's why people talk about larger things are weaker. Okay. And actually the Weibull distribution can be shown if you make a simple theoretical model of a micro thing that instantly causes rupture. You can show that it should follow a Weibull distribution. So key thing, bigger grains are weaker. Okay. Again, no one's done these type of studies on solid things, so we're going to do the best we can using the data of that behavior. And we're going to notice that at the scale of a grain, and you look very carefully at a contact, that's like a structure now at this scale. That's actually 2 stand grains with cement in there, right? I mean, if I didn't have a length scale here, I could say, my God, this looks like the moon. These are like 2 of the moons that are pushing together, right? I mean, this is like a rock mass is what I'm saying here. We always think of grains, we look at them from really far away. Oh, it's just a simple, obvious thing. They're all the same. No, they're not. They're completely crazy. This is part of the reason why the bigger ones are weaker, because they have all these weird initial defects and stuff in them. Okay, so I'm going to say, how does a grain break? I'm going to pretend that a grain is a rock mass. And I'm going to pretend that I took a whole bunch of cores out of this thing, and I did a whole bunch of UCS tests and triaxial tests. And if I did that for rock specimens, sorry, I'd get a strength envelope, a Hook-Brown strength envelope. And this is, we talked a little bit about this. This is stress sigma 1, sigma 3 space, principal stress space. This is the strength in the triaxial test. That's a UCS test. If you apply compression, it gets stronger. This is the tensile strength. And so I'm going to assume that it fits this. So there's going to be 3 parameters in my breakage model. And these are the Hook-Brown parameters. This is the Hook-Brown equation. It has a M, it has a UCS, it has a tensile strength. Okay. And so this is what we're doing in our model. And we won't worry about anything else. And what happens then is that when the stress is outside of this intact region, as soon as the stress gets out there, it breaks. Boom, next time step, it suddenly turned into 2 rigid blocks. It got split through the centroid, and the orientation of that split plane is perpendicular to sigma 3. Okay, it's the least amount of compression. That's how it wants to orient itself. This is what rock does. So this is the breakage scheme. Okay, and this is just mentioning the size effect business about the strength. We have to actually make our strengths follow this size effect. We have to make it so that the bigger grains are weaker. And this actually can be traced way back to Leonardo da Vinci. He took a bunch of ropes of different lengths and poured sand in a bucket underneath. And he found that the longer ropes failed sooner. The longer ones were weaker. And this is the idea of you have more material. If the material has flaws, the more you have, the more likely you are to encounter a critical flaw. And so this is what this crazy size effect is. And so this is saying, if, like, look at the green curve, the grain size gets big, the strength gets small. The grain size gets smaller, the strength gets bigger. And there's a parameter that controls which curve you're going to get. Okay. So in the end, then, this model, kind of crazy. It has 18 parameters. Count them up. So for the deformability, remember, contact modulus, contact Poisson ratio, Weibull shape factor. This is showing how the contact modulus varies based on shape factor. So you get the heterogeneity induced tension. Microcrack fabric. Well, we're going to say you can have gaps. And that means if you're going to have gaps, you got to say what fraction of them have gaps. What fraction of them here? This is basically a gap with no bonding, a gap of 0. So I call it a slit. And this is actually, they're perfectly touching and bonded. So you have to be able to describe what % of them is each of these. And what's the mean size of the gap and how it varies? Interface strength, right? Tensile strength, cohesion to tensile strength ratio. This is basically the standard sort of, this is like the parallel bond model. But in addition, this interface strength is going to be able, itself is going to have a variation. This is the tensile strength. This is actually the probability density function that's measured by doing a test on 20 lactobond granite specimens. Again, we think of a tensile test. Oh, we do tensile tests. We get 7 MPa. No, we don't. We get 7, we get 8, we get 3. Well, maybe not 3, but we get some distribution. And lo and behold, lactobond granite tensile tests get fit very well by a Weibull distribution. Okay. And then the grain strength. There are these different parameters related to the grain strength and different ways. It's always going to split. It's always going to split perpendicular sigma 3. Okay. So there we go. That's our model. And this model then, you may recall when I was talking about the physics of what happens during a UCS test on a compact rock, you go through these stages of damage. And these stages of damage are quantified by these different types of stress thresholds. And so we call these characteristic stresses. And I'm not going to go back again over that. Okay. It turns out that a bunch of guys, Eberhardt and others in 1999 did a whole bunch of tests on pink lactobond granite and actually measured all of these things very, very carefully. Again, hardly anybody ever measures all these things. Usually all they care about is the slope, E, and the UCS. But these guys are looking at this really carefully. They measured all these things. So I actually have real data. I'm not aware of any other rock where all of these things have been measured. So there we go. Pink lactobond granite. So I actually have data I can compare with to see if the model, it's not just a hand-waving qualitative model. And so here we go. There it is. That's pink lactobond granite. These are the different characteristic stresses. They correspond to all of these along this curve. In particular, I'm pointing out here, this is when they observe cracking in the grains of quartz. That's here. So notice you're getting cracking before the whole thing breaks. Okay. Notice also the tensile test has a lower modulus than the compression test, and we've talked about this. They called it a bimodular rock. We can choose a set of microproperties for this model that are reasonable, that are defensible, that allow us to match all of these things. It matches this response, the general characteristics of first you get gaps closing, then you start to have not much of anything, then you start to get cracking all over the place. That's horizontal, that's vertical, it's aligned with compression. Then eventually you get breakage, then you get volumetric, all this stuff. Okay, it's all behaving like that. Okay, and the reason is because this model is actually built at the grain scale. So this is what these models look like. We did 2 specimens. This is the size, 31 millimeter, 61 millimeter, exact same microstructure, just bigger hunk of it. The real rock was done on 61 millimeter cores. The real rock had grains that were between 3 and 4 millimeters. That's what we did. So we got the real grain size. We got the real core specimen size. We should actually match the real behavior during that test, and we do. Okay. And then here's all these values of those different parameters, and we're not going to talk about this. You can read the paper. We talk all about this. Like we had to put in gaps. And the gap sizes we put in are very similar to the gap sizes of these large aspect ratio cavities. So that's why I mean defensible. We didn't just go and put crazy values in for gaps. Like these are completely reasonable and very likely to be. These are the kind of gaps that are in westerly granite. So we're assuming there might be similar gaps in this pink lactobond granite. Okay. Here's the behavior. This is the model. At the end, this is a direct tension test. Stress strain goes up. There's a little bending over. There's cracking. And then it brittly fails. These are grains that have split. So during the direct tension test, there's little cracks here. Those are interface breakages. And then eventually, and a few grains that split, very few, and then it localizes into a fracture surface like this, where all these interfaces have broken, and that's what corresponds to that. Okay. This matches the crack thing. You know, we get the tensile strength, and we get the tensile modulus of 44. Then we take the same thing and do a UCS test, and this is our stress strain curve. Notice it stiffens. This then is our what they call that crack closure stress. It starts crack, da 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 da. Here's this other stress. Here's where our grains start to break, and here's the UCS. So all these things are matching. And we're also measuring these characteristic stresses in the same way that you would measure them for a laboratory specimen. So we essentially built, as close as possible, a one-to-one mapping of a real laboratory specimen. And we measured the same things that you measure in a lab. We didn't use measurement circles and things. We actually measured the way you would measure it in a lab, and the way you would process the data from the lab to back calculate these characteristics. We did all that same stuff. Okay. This is what's happening. If you're looking down the specimen, this is the UCS test. So the stress strain goes up. It's pretty brittle of a failure. At this point, we stop the test and we look down the axis and we see that it's axially, all these columns, and it's wanting to bulge out. It's not confined. So these surface guys are also blowing out. Okay. If we take the same specimen and apply confinement around there, that's what we did here. Notice the stress strain curve. They have the same y-axis, same x-axis. The peak higher, and there's a residual result, just like in the lab. Now, of course, it's trying to bulge out like this, but it can't because it's confined. So we see this. Okay. And this is the craziness. If you actually look at the damage in the specimen at this point, basically when it's completely failed in a UCS test, and it's crazy. There's a huge number of broken interfaces, and these are only showing the broken grains. Most of the this damage is happening after the peak. But again, it's reasonable. It's like what we see in the real rock. There's a huge amount of damage in that specimen at the end of that thing. And this is showing how the grains are splitting parallel to the compression, which is what also is happening. So to sum this up, this is a very good model at the grain scale. And it's because it has the microstructural mechanisms that really occur at the grain scale. I'm not aware of any additional microstructural mechanisms that are occurring at this scale. Okay. And we were able to demonstrate with a defensible set of micro properties, we could actually match in full detail the behavior during a UCS test. Okay. So this gives us pretty good confidence that this model could be applied now to do all kinds of study at the grain scale of damage processes. And again, we have that modeling package. You can do this with 2D, with 3D, and use it for your research. The bigger picture, this is for you and King here, because you might use this. The bigger picture is at the grain scale, we got a good model. Okay. And in the future, if speed of computation continues to increase, we should potentially be able to actually model a field scale thing by just putting this stuff everywhere. Can't do that now. It takes too many particles. And so thus, currently, we have to scale up the sizes. And that's not really well understood. Okay, so that's an open area of further research. And the final closing words of wisdom here for this kind of modeling is the more you can match the actual features of the microstructure, because those are the things that control everything, the closer you should get to the macroscopic behavior. And this kind of work still has a lot of areas to be explored to achieve this. And maybe some of you can be workers in this field and maybe even work a little bit with me, and we can move this research forward. And so there we go. We made it to the end of the talk. We actually made it to the end of the course. And